Hello and welcome to Monochemistry. Today we're going to look at heating and cooling curves. This one that you see here is a heating curve, and we're going to look at how it works a little bit, and also we've talked about how to calculate a heat change between areas like C and D, but how do you calculate a heat change in here? Because obviously there is a heat change, but there's no temperature change. Okay, so energy is still being distributed, but temperature is not being affected. So first of all, we're going to talk about why that is, why during a phase change the temperature isn't affected, and also how to calculate a Q value for that particular sequence. Okay, so let's talk a little bit about this. So if this was, let's say, water, you could see, so this would be water as a solid, and what I want you to do is I want you to draw this graph exactly as it is. Okay, so temperature versus time. Okay, you're going to label all these things, A, B, C, D, E, F. Go ahead and draw this, just rough in your notes, and we're going to label each of these things. Okay, so A, okay, from A to B is a period of time where the solid is being heated. Okay, so like if it was ice, it would be ice being heated up. Okay, so ice is being heated up. At B, that's when the solid starts melting. Okay, so between B and C, the solid is melting. That's our phase change. Okay, so that's the melting phase change. From C to D, the liquid is being heated up. And then from D to E, or at D, I suppose, that's when the liquid starts to boil. And from D to E, it's when the liquid is being turned into a gas. It's the second phase change. And then from E to F, the gas itself is being heated up. Okay? So draw that, label each of those parts, from A to B, B to C, C to D, D to E, and E to F. And from there, we will go on. Make sure you note that this is a phase change, and this is also a phase change. Okay, so this is the solid to liquid phase change, and this is the liquid to gas phase change. Okay? So why? Why does the temperature increase here? I mean, we're adding heat, so this is constant heat. So we're adding a constant heat, and the temperature is going up. But then all of a sudden, when we get to this point, which is known as the melting point, it doesn't do anything. Well, it does, but it doesn't do anything according to temperature. The temperature stays the same. Why is that? And the same thing up here. Why does the temperature stay the same between D and E during that phase change, okay? So D to E, and D is the boiling point. Okay, the temperature at which the substance boils, and B is the temperature at which the substance melts. So you can label those two. Okay, so let's talk about this. Recall that solids are densely packed materials, typically speaking. Liquids are more loosely packed, but still fairly close together, and then gases are completely separated. Okay, so as I increase the temperature, I can convert a solid to a liquid to a gas. And as I increase the temperature, we also know that the motion of the molecules, or the particles, increases. In other words, the higher the temperature, the faster the particles move. Okay, so both of those things we know. Last year in grade 11 chemistry, we talked about molecular interactions, also known as intermolecular forces. Okay, and intermolecular forces are forces of attraction between molecules. Okay, so if we take a look here, these particles are very tightly packed together, so there would be forces of attraction between them. In order to separate them, we might have to kind of break some of those forces of interaction between them. However, to go from a liquid to a gas, we have to completely break all of the interactions, all of the intermolecular forces that occur between the particles. Because otherwise, how are we going to get them all separated like that? Okay, so we have to break some interactions to go from a solid to a liquid, but we have to break all of the interactions to go from a liquid to a gas. And anytime you're breaking bonds, whether they be strong, weak, whatever, anytime you're doing that, you have to add energy. Okay, so let's think of it this way. I have a solid, I don't know, a piece of ice. I heat it up. The temperature starts off at minus 10 and goes up. As I heat the solid, it goes up. When it gets to 0 degrees Celsius, Instead of actually heating up the solid, now I'm melting it. And in order to melt it, I need to start breaking some of the interactions that are occurring between the solids, the particles in the solid. And in order to do that, these need to absorb energy. If they're absorbing energy, there's not going to be any temperature change. Fast forward, we've got our liquid. Heat the liquid up. It's going to go up and up and up until it gets to its boiling point. At the boiling point, it's going to require a lot of energy to break all of the interactions that happen to be there. And once I break those interactions, then I get my gas particles, but it's going to take some time. Again, I'm shooting energy into it, into the liquid, at the boiling point, but it's absorbing that energy, and then the temperature is staying the same. Okay, because that energy is going into breaking those interactions. Here's a little analogy for you. Okay, so imagine you have a balloon, an unblown up balloon, just a piece of that rubbery kind of balloon stuff. Stretch it out as far as you can stretch it without breaking it. Okay, so as you start off, it's in between your fingers. You pull it, you stretch it, you stretch it, you stretch it, you stretch it. You're using force to stretch it, and you're going to get to a point where you can't stretch it anymore without breaking it. Okay? Now, keep pulling. Does it break right away, or does it require a little bit more, and bang, it pops? Okay? The pieces of rubber pull apart finally, but it takes quite a bit of energy. You're not stretching it any further than you did before because you've already stretched it as far as it can go, but it's going to require a little bit of energy for the interactions between the rubber to break apart and to rip that balloon apart. Okay? That's what's happening in this situation here. It's exactly what's happening in this situation. You're adding energy, it's heating up until it gets to a point where it has to absorb a bunch of energy in order to break. That's what we're doing in this situation here. So how then do we calculate the actual values that occur at the melting and the boiling points, or at the melting and the boiling points? How do we calculate the Q value? Because we're obviously adding heat. How do we do that? Well, here's the formula we use. Q is going to be equal to N, which is the number of moles. So heat is equal to the number of moles times the change in enthalpy. Okay, now the change in enthalpy, delta H, we haven't really talked about that in class yet, but it's a type of heat change or energy change, okay, that occurs. And the cool thing about a particular substance is that the energy change for the boiling and the melting process are generally standardized if we take it at standard conditions. So, for instance, we would put the delta H standard, that little circle means standard, of this is melting. Okay? And that would be a particular number for a particular substance. And the same thing up here, you would have the delta H standard of, it would either be evaporation or boiling. You get the idea. We'll just put boiling for now. Okay, so delta H standard of that. So those are numbers that you already have. So all you need now is to figure out how many moles you have. Okay, and sometimes in some questions you'll be given grams. Fine, you can calculate, if you know the substance, you know the chemical formula of the substance, you can convert grams to moles, no problem, using the molar mass. Sometimes you'll just be given the moles. So basically the amount of heat that's transferred is equal to the number of moles of the substance times the amount of energy it takes to cause either the melting or the boiling of the substance. Now, take a look. Here's a question I want you to think about and answer. This part here for melting is a lot smaller. The amount of time it takes is a lot less than for boiling. Based on what I've talked about in this video, why do you think that is? Why does it take longer to boil something than it does to melt something? I'll leave you with that. But that, in a nutshell, is how we interpret these particular processes and how we eventually will calculate a Q value or a heat value for for these phase change processes.